Yet another use of the ideal gas equation is for gas stoichiometry. We talked about stoichiometry twice before in Chapter 3 and Chapter 4. In Chapter 3, we talked about stoichiometry in a solid phase. In Chapter 4, we talked about it in a solution phase. And nothing changes when you go to gas stoichiometry except for another starting point and another possible ending point. Just as before, our diagram is the same. We have the 4-box system, and then we have filled into that some things. So in the first box, we have grams given. Second box, we have moles given. Third box is moles wanted. And then the last box is grams wanted. To go from grams given to moles given, we multiply by 1 over the molar mass. To go from moles given to moles wanted, we multiply by what we want over what we have. And to go from moles wanted to grams wanted, we multiply by the molar mass over 1. Now in gas stoichiometry, we have 2 new boxes up there, and it's the same boxes that were there in solution stoichiometry, but what is in them is different. In this equation, we are given P, V, and T in there. Given a pressure, given a volume, given a temperature, we can use the ideal gas equation and solve for moles of a given substance, just like we did in one of the previous examples. So to get from PV and T, we have N equals PV over RT here. So now I can start with grams given. If I have a mass of something, I can start there. I can start with moles given, or I can start with the pressure, volume, and temperature given. Important to note that you must be given all 3 variables to start with that box. We can also end with pressure, volume, and temperature. All right, again, we're going to use the ideal gas equation there. In this case, if we're asked to find the pressure of a new gas, or the volume of a new gas, or the temperature of a new gas, we can find it, but we would have to be given the other conditions. So if you're solving for temperature, you would have to be given the pressure and volume in the problem as well. All right, so let's look at some examples here of how we use this. Our first example is talking about the safety airbags in a car. If you've never seen the airbag in a car go off, that reaction is attributed to the decomposition of a chemical called sodium azide, NaN3. If an airbag has a volume of 36 liters and is to be filled with N2 at a pressure of 1.15 atmospheres at a temperature of 26 degrees Celsius, how many grams of NaN3 must be decomposed? When we start with stoichiometry, we always said the first step is to balance the equation. In this case, our equation is already balanced. Step 2 is to write down what we know and what we want to know underneath the equation. All right, so what do we know? We know the N2 is going to have 36 liters. We know the pressure of the N2 is going to be 1.15 atmospheres. And we know the temperature of the N2 is going to be 299 Kelvin. All right, so that's all we know. We want to know how many grams of that substance we're going to have to start with to do that, to get those conditions. All right, so given what we know, looking at our diagram, we are not starting with grams given because we don't know the mass of anything. We're not starting with moles given because we don't know the moles of anything. But we do know the pressure, volume, and temperature of something. So we are going to start here. And we're going to end over here. So first, we need to take and get moles of N2 by multiplying N equals pressure, 1.15, times volume, 36, divided by R, 0.08206, divided by T, 299 K. All right, so when we solve that, that will give us moles of N2. All right, so let's put that into our calculator. 1.15 times 36 divided by 0.08206 divided by 299, and we get 1.69 moles of N2. All right, so now we know moles of our given substance. We need to go from moles given to moles wanted. So we need the ratio, what we want over what we have. Here's what we want, here's what we have. 2 NaN3 over 3 N2. All right, now we're here. To get to grams wanted, we need to multiply by the molar mass. The molar mass of NaN3 is 23 for sodium. 3 nitrogens is 42. So it's 65 0.0 grams per mole. All right, so from there, again, we plug in our calculator. We're ready to do our stoichiometry. 1.69 times 2 divided by 3 times 65 gives me 73.2 grams of NaN3. Now, the first engineer who designed an airbag probably did a calculation very similar to this. And why is it important? Well, what would happen if we had too much sodium iodide into that container or in the steering wheel? Well, when it decomposed, you produce too much gas in the steering bag, or the airbag could explode. If you don't have enough, it might not inflate enough, and it could not protect you in a crash. Let's look at another example, and I'd like you to do this example on your own